All right, here we go. This is lesson 13, and we're going to be looking at uh, orbital filling diagrams, which is the ones without valence only the valence electron, without all the other electrons. And from that, we are going to look at metal ionization. Now, metal ionization is, I guess, different from making covalent bonds because, of course, we're just losing electrons. From the last year, we know that they're good reducing agents, so they give away electrons. So they're not sharing anything; they're just losing them. All right. So we're going to be exploring how they are lost. All right. So having said that, yeah, let's get right into it. So using orbital filling diagrams predict the possible oxidation states of scandium-21, tin, and tungsten. All right. Now, at this point, usually there's still a bit of confusion, and that's normal. Like, don't feel bad if you're confused at this point, because everyone's confused at this point because of the nature of it. You're learning something that's new, and let's face it, it's not entirely logical. We're not talking about logic right now. We're talking about what the reality of the universe is. All right. So, and that's what quantum mechanics is all about, and why even the greatest of scientists struggled with this stuff. They truly did struggle with it. Okay, here we go. Yeah, so let's do scandium-21. We're going to look at its valence electrons. So we're going to use the 4s orbital and 3d orbital. And we know that the 4s comes before the 3d, just because they're just slightly closer to the nucleus. All right, so, and those are, that scandium-21. So we left out everything up to argon. We didn't include it, and that's what we have. So we want to predict probable oxidation states. Not that they are exactly going to be it. We might make mistakes, but hey, there we go. Well, if I was to say, if I was to look at this, I would say, well, definitely that 4s would, let's change colors here. That 4s might come out first, make a 2+ charge, and then perhaps that next electron would come out next, and that would make a 2+ and 3+ charge. That would be a reasonable prediction. It is wrong. This is the only charge is 3+, right? It doesn't form compounds with a 2+ charge. Now, you can't really know that. We're just saying what was probable here. I mean, if you look at the 3D orbitals, the other 9, so after scandium, titanium, vanadium, chromium, blah, 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 all the way to copper and zinc, they all have a 2+ charge because the electrons all come out of the 4s, but scandium doesn't, all right? It just happen to be, these 3 electrons happen to be very, very close to energy there. So they come out all at that same level of energy, and we form a 3+ charge. Okay, next, tin. So this would be our, let's change color again. We've got our 5s over here and our 5p over here. And this would be our 4d. Now, we don't have to include this, all right? So I did that sort of intentionally to show that we don't really need this. Like, all those electrons are here, but they're not true valence electrons. In energy, they belong between the 5s and the 5p, but they're not true valence electrons. So we don't need to include this in our orbital filling diagram. The 5s, of course, and the 5p, of course. All right, and we would go back to our previous noble gas, which would be, in this case, that would be krypton. All right, so for tin, well, the highest energy orbital would be the 5p, would be higher than the 5s. So that might give us, sorry, let me just change color again here. That might give us a 2+ charge. And then over here, that would give us a 4+ charge. And that is what we observe in nature. So in nature, tin forms 2+ charges, like tin 2 chloride, and it forms 4+, tin 4 chloride, or oxide, or sulfide or bromide or whatever it is you want. All right, so that's what is going to happen when they lose. So what you see here in theory actually matches what happens in the real world, and that is the test, right? Is what actually do you get? I mean, you can argue that scandium should have a plus charge. It doesn't, though. All right, nature just doesn't give it to us. All right, and that would mean, do we have to go back and retool our theory? All right, so we've got to retool this a little bit. Okay, so last one is tungsten. And just to locate that on the periodic table, you can see that it's that 5D4. So that would be that 5D4. So here would be tungsten, and tungsten is, whoops. All right, so we could look at a couple of different things, and we could say, yeah, does tungsten have a 2+ charge? All right, oops, I didn't write these down. So that's our 6s and our 5D. All right, and we've left out the 4F14, right? So we've just left that to the side. I mean, that would slip right in here, but we're not going to include it. So the 4F14 electrons, we don't really need those. So we're not going to use them at all. So tungsten, we can say, would have a 2+ charge. We would make that prediction, sure, all right? We'd make that prediction. And then we could also have these other 4 electrons here. And I suppose we could make the prediction that they all come out 6+, right? Could be. Anything in between, possibly, all right? So let me just leave that with you and look up to see what you think tungsten could possibly have. And we would say off the bat that 2+ and the 6+ makes sense, but do they have any other ones? Yeah, go look that one up. All right, so that is what we have here with ionization of metals. When it starts to get into, d orbitals and f orbitals and p orbitals, sometimes it can get a little bit hazy, but hopefully that clarifies things.